Welcome to For the Love of Physics. And a really special welcome today to all the students at Ishik Boys High School, especially if you're in Mr. Jigger's physics class. Today we're doing a deep dive into something fundamental solids and their properties. Think about, well, everything solid around you. Ever wonder why some things bend and others break?
Exactly. Our mission today is to unpack what holds solids together and how they react when you push or pull on them. We want to make understanding these core physics ideas like rigidity and elasticity a bit easier. Think of it as a helpful guide to what you're learning in class.
Yeah, we'll be looking at what makes a solid, well, solid in the first place. Why can some things bounce back after being squashed while others just stay put? We'll touch on things like stretching a rubber band, the sheer strength of a bridge. We'll get into rigidity, elasticity, tension, stress, strain, and this thing called Young's modulus. Sounds like a lot, maybe.
But we'll break it down. It's all connected, and it helps explain so much about the physical world.
Okay, let's start right at the beginning then. When we look at a solid, like say, a piece of metal, or even just a sugar cube, it seems so fixed, permanent almost. What's actually going on inside at that super tiny invisible level?
That's the key question, isn't it? Solids hold their shape because deep down at the atomic scale, they're made of atoms or molecules arranged in these really regular organized patterns, like a grid almost. And these particles aren't perfectly still. They actually vibrate around their fixed spots.
Both vibrate.
Yeah, tiny little jiggles. But crucially, these movements are really small compared to the distances between the particles themselves. They mostly stay put in their formation.
So it's like tiny, super organized dance parties where everyone's kind of vibrating but stays in their designated spot.
That's a fun way to put it. Yeah, pretty much. And this ordered structure is what stops them from just flowing away like liquids or gases.
Okay, that makes sense. So how does this arrangement, this atomic dance party, affect the properties we can actually see and feel, like how strong something is or how it conducts heat?
Well, that arrangement depends on a few things, like the shape of the molecules themselves, how strongly they're attracted to each other, those interatomic forces, and importantly, temperature.
Temperature affects the vibrations.
Exactly. More heat means more vigorous vibrations. And yeah, this structure influences almost everything. Mechanical properties like hardness or flexibility, but also electrical properties, thermal ones, even magnetic characteristics. It's why, different solids behave so differently. Think diamond versus rubber. Very different atomic arrangements and forces.
Right, okay. Now, we know from Newton's laws that forces can change things, change motion or even shape. But some solids, like huge train rails, seem to just ignore this. A massive train rolls over, and they barely seem to budge.
That brings us to the idea of a rigid body. In physics, we define a rigid body as something that essentially preserves its shape perfectly when forces act on it. Train rails are a great example. For all practical purposes, we consider them rigid because the deformation under the train's weight is incredibly small.
Okay, rigid. But not everything solid is rigid, right? I mean, you mentioned rubber,
Yeah.
or think about a bag of sugar. It's solid, definitely, but you can squish it and change its shape easily.
Correct. That's a really important distinction. All rigid bodies are solids, but not all solids are rigid.
So what's the secret sauce for the train rails then? What's happening at that atomic level that lets them resist deformation so well compared to the sugar?
Well, even in things we call rigid, there are minuscule displacements when force is applied. Nothing is perfectly rigid in reality. But what prevents large deformation in materials like steel rails are incredibly strong repulsive forces between the atoms or molecules. When you try to push them closer together with a huge force, like the train's weight,
They push back hard.
exactly, they push back very strongly. Think of trying to force the north poles of two strong magnets together. There's this powerful resistance. It stems from fundamental physics, keeping atoms from occupying the same space. These strong internal repulsive forces are what give the rails their immense strength and stop them from visibly bending.
Fascinating. So even the stiffest things have a little give, microscopically.
Right.
Okay, so some solids are rigid. What about the opposite end? The ones that deform quite a bit but then snap right back. Like, picture a tennis ball getting absolutely flattened by a racket.
Now you're describing elasticity. Elasticity is the property of a body that allows it to restore its original shape and size after the deforming forces are removed.
The tennis ball is perfect. It gets squashed,
Massively deformed on impact.
but then instantly pops back to being round. That's elasticity in action.
Precisely. Or think about your mattress. You lie on it, it deforms.
Makes a nice comfy dent.
Right. But when you get up, it returns to its flat shape. That's elasticity too. Contrast that with, say, a lump of clay. You deform it, it just stays deformed. That's plasticity, the opposite.
Okay, got it. Elasticity is the spring-back ability. You also mentioned springs,
Yeah.
like spring with a weight on it.
Yeah, a vertical spring with a mass attached is a classic example. It stretches, might oscillate a bit, but when the force is removed or it settles into a new equilibrium, it has demonstrated its ability to deform and potentially return. That's elasticity at work.
Okay, this makes sense. We have rigid things that resist change and elastic things that deform but bounce back. But physics likes numbers, right? How do we actually measure how much something is being stretched or squashed? How do engineers know if a cable is strong enough?
Absolutely. We need to quantify this. This is where we get into the tools engineers use every day. Let's start with tension. Tension is basically the pulling force transmitted through a string, a rope, a cable, or a wire when it's pulled tight by forces acting from opposite ends.
So if I pull on both ends of a string,
There's a tension force inside the string pulling back. It's an internal force. Imagine a tug of war happening within the material itself. And usually we assume this tension is uniform all along the wire, assuming the wire's own weight is negligible.
okay, so tension is the internal pull. What about how, concentrated that pull is? Does it matter if the wire is thick or thin?
Great question. That leads directly to stress. Stress is defined as the force applied per unit of cross-sectional area.
Force per area, like pressure.
Exactly like pressure. The units are the same. Newtons per square meter, and M, which we also call pascals. It tells you how much force each little bit of the material's cross-section is handling.
So pushing a thumbtack in lots of force on a tiny point means high stress.
Perfect example, high stress concentration. And there are different kinds, like you mentioned. Tensile stress is pulling it apart, compressive stress is squashing it together, and shear stress is like scissors cutting paper, forces parallel to the surface.
Tensile, compressive, shear. Got it. Okay, so stress is the internal force intensity.
Right.
But what about the result? How much does the thing actually stretch or shrink?
That measure is called strain. Strain is the measure of deformation representing the displacement between particles in the material body. Specifically for stretching, it's the elongation, the change in length divided by the original length.
Ah, okay, so if I have a 1 meter rubber band and I stretch it to 1.1 meters.
The elongation is 0.1 meters, the original length is 1 meter. So the strain is 0.1 divided by 1, which is 0.1.
And it's a ratio, so no units.
Exactly. Strain is dimensionless, just a number representing the proportion of deformation, how much it changed relative to its original size.
That's neat. So quick question then. Does the original length affect the strain or the thickness? If I have a really long, thin wire versus a short, thick one.
Excellent points. Let's take length first. If you have two wires of the same material and thickness, but one is twice as long as the other, and you apply the same tension, the longer wire will stretch more in total distance. Its absolute elongation will be greater.
Makes sense. There's more material to stretch.
Right, but the strain, the elongation per unit length will be the same for both wires. Each meter of the wire stretches by the same proportional amount. Think of it like identical springs connected end to end.
Okay, same strain, different total stretch. What about thickness, the cross-section?
Thickness has the opposite effect, sort of. If you have two wires of the same material and length, but one is thicker and you apply the same tension.
The thicker one stretches less.
Correct. The thicker wire elongates less. Because that same total force, tension, is spread out over a larger cross-sectional area, each part of the material feels less stress.
Like springs side by side in parallel. Each one carries less load.
Precisely. So thicker wires resist elongation better under the same total force. Less stress leads to less strain for the same material.
This is clicking into place. Stress is the force per area. Strain is the relative deformation. Now, is there one magic number for a material that links these two? Something that tells us intrinsically how stiff it is, regardless of shape?
Yes, there is. And it's incredibly important in engineering and materials science. It's called Young's modulus, E. Young's modulus is simply defined as the ratio of stress to strain within the elastic limit of the material. So E equals stress strain.
Stress divided by strain. Okay.
It's a fundamental property of the material itself. It tells you how resistant that material is to being deformed elastically when you apply stress. Think of it as a measure of stiffness.
So a really high Young's modulus means it's really hard to stretch or squash, like steel.
Exactly. Steel has a very high Young's modulus. It takes a huge amount of stress to cause even a tiny bit of strain.
And rubber would have a really low one.
Yeah.
Because a little stress causes a lot of strain.
Perfect. Rubber has a very low Young's modulus, and since strain is unitless, the unit for Young's modulus is the same as the unit for stress, Nm or pascals.
Wow. So engineers use this number all the time.
Constantly. It's crucial for choosing the right material for a job. Need something strong and rigid for a bridge girder. Pick a material with a high E, like steel. Need something flexible for a shock absorber or a phone case. You look for materials with lower E values, but maybe other important properties too. It allows engineers to predict exactly how structures and components will behave under load. It's why they could be confident those train rails would hold up. They knew the Young's modulus of the steel used.
Amazing how it all connects back.
Yeah.
Okay, wow, we really covered some ground there. Let's quickly recap. We started deep inside solids, looking at those organized atoms vibrating in place, giving solids their shape.
And we saw the difference between rigid bodies, like train rails that barely deform, and elastic bodies, like that tennis ball, which deform but spring right back.
Then we got into measuring things. We defined tension as that internal pulling force,
Stress as the force per unit area, kind of like the internal pressure.
and strain as the relative change in length, that unitless measure of deformation.
And finally, we tied stress and strain together with Young's modulus, E, that key number telling us how stiff a material is, how much it resists stretching or squashing. Super important for building, well, almost everything.
So here's a little challenge for you to think about. Consider the strings on a guitar or a violin. When a musician tightens those strings to tune the instrument, think about all the concepts we discussed. What roles do rigidity, elasticity, tension, stress, strain, and the Young's modulus of the string material play in that whole process? And maybe even think about how that relates to the sound the string makes.
Yeah, give that some thought. It connects a lot of these ideas.
Thanks so much for joining us for this deep dive into the world of solids.
Stay in contact with your physics teacher. Stay creative.